Well, it's a great pleasure to be here tonight to talk to you. I am very happy. I want to thank the organizers for the invitation and thank the museum for hosting, but I most of all want to thank you for taking time this evening to come and hear about the kinds of work that we do in cosmology. So I'm going to be telling you tonight about a very mysterious phenomena known as dark energy and how we try to investigate this using sound waves that propagate in the first 400,000 years after the Big Bang. And I'm going to be focusing the talk both on some of the theoretical motivations of the work and some of the physical phenomena, but also very much on the experimental technique that we use to investigate dark energy. So the base outline of the talk is I'm going to start by giving an introduction to cosmology. Obviously, cosmology is a very big field, and I'm going to try to focus in on the part that I need for this lecture. And then I'm going to tell you about this phenomena called baryon acoustic oscillations. So acoustic means sound. It is very much like the sound waves propagating in this room. And I'll be telling you about how we use these to measure the scale of the universe. And then I will introduce you to the survey that I've primarily been using, the Sloan Digital Sky Survey, and tell you about how we've detected these sound waves in the Sloan survey and what we've learned about cosmology from that. So to get started, the main question here is, what is the universe made of? So it's a very fundamental question, obviously, very basic question that we'd like to understand about the universe. And as you may know, either from the popular literature or from the speakers in the last 2 weeks, this has turned out to have very surprising answers. It turns out that most of the universe is made of stuff that's not the familiar protons and neutrons and electrons that make up us. The first evidence of this came from the study of what's called dark matter. So we learned, we've known for a while, that when you look at the motions of stars inside a galaxy, the stars are rotating around the center of the galaxy too quickly to be bound by the gravitational pull of the stars that we see. And we infer from that there must be additional matter, there must be additional gravitating matter in galaxies that hold the stars together. And similarly, when we look at clusters of galaxies, the galaxies within those clusters are moving around the cluster centers too quickly. So Gary Bernstein gave a talk in this room 2 weeks ago on this subject and pointed out that in fact we're now at the point where we can infer this mass directly by the bending of light. Here is a picture of a cluster of galaxies, and these blue galaxies that you see are actually, those four are actually the same galaxy far behind the cluster and the light from those galaxies has been bent by the cluster. And when you figure out how much mass you need to actually bend the light, you infer a much more mass, factor of 10 to 30 times more mass than what we see in the stars. Well, we've also figured out that this extra mass is not some familiar stuff. It's not that there's little, dark books or dark cars out there floating in space. This is actually some exotic form of matter that we're still looking for. But the question is, how much is there? And when you study the motion of stars in a galaxy, you can figure out how much dark matter there is in a galaxy. When you study the motions of galaxies in a cluster, you can figure out how much material there is in the cluster. But when you want to figure out how much stuff there is in the universe as a whole, you have a bigger problem. And so a way that we try to do this is by measuring the expansion rate of the universe itself, that the dark matter, the extra material in the universe, will pull on the expanding universe. And so if you have more material in the universe, you would expect the expansion rate of the universe to be slowing down over time. And that's the test that people set out to do. Now, I mentioned the word expanding universe, and that dates back to the 1920s. But what does it really mean? So what we mean is that when we measure, we can measure how fast galaxies are moving away from us. And we do this because the atoms in galaxies, or atoms in this room for that matter, and the fluorescent lights in this room, emit light at very particular wavelengths. So when you take a spectrum of a galaxy, you might see, as you separate the light from red to blue, you might see characteristic frequencies or wavelengths that have extra emission or extra absorption because of the quantum properties of the atoms that make up those galaxies. And when we look at distant galaxies and take their spectra, we find that these lines are characteristically shifted to the red. They are shifted to longer wavelength, as if the light has been stretched in its wavelength as it travels to us. And this can be interpreted as a Doppler shift. You know, if you're out on the road and an ambulance is coming towards you, then the pitch of the ambulance seems higher as it's moving towards you, and as the ambulance passes you, all of a sudden, you know, the pitch shifts lower, and you can infer that the object is moving away from you. And light does the same thing, so we can measure this Doppler shift, and we find when we do this that all of the galaxies, with one exception, but all the galaxies are moving away from us. And the further they are away, the faster they're moving. So this is a famous result known as the Hubble relation, and it tells us that the universe is actually expanding, that the space between the galaxies is getting larger, and the size of the universe today, if you were to have lived, you know, 8 billion years ago, all the galaxies would have been half the distance apart, and on as you go down towards the early times. So this recessional velocity is also known as the red shift, because the photon wavelengths are shifting to the red. And we use redshift because there's a clear association between the speed that the object is moving away from us and the distance to the object. And because distance is related to light travel time, it's also related to how long ago the light was emitted. So there's a clear one-to-one relationship between the redshift and the time that the epoch of the universe that you're looking at. So astronomers sort of interchangeably use the word redshift not only to measure this Doppler shift, but also as a label of time in the universe. So I will very often, well, I don't know if I'll say it, I'll try not to say it too often in this talk, but if you hear an astronomer say, oh, we observed a galaxy at redshift 1, they're telling you that the light was shifted by this amount, but they're also telling you when they think that galaxy was being observed. Okay, so let's think about what it means to weigh the universe by measuring this deceleration. So if we have a plot of the size of the universe, where 1 is the present day size, and the age of the universe, where I've marked 0 as the time of the present day, then if the universe was not feeling any acceleration or deacceleration, then you would expect to just have some straight line. In other words, you would have had some boom back here, and everything would just be ballistically expanding out. If instead the universe has some deceleration, then you might expect a more rapid expansion at the beginning, and then things would be slowing down. And the point I want to get across to you here, so as you have more matter, you would expect more deceleration. But the other point is that the amount of time, and hence distance, that an object appears away from us at a given redshift would be changed. So if you have a universe with more matter in it, more deceleration, then you would expect objects at a given redshift to appear closer. And so you have this relationship between measuring distance to a given redshift and measuring the expansion history of the universe and measuring the amount of material in the universe. So this is a test that astronomers have been set out to do for 30 or 40 years, and they finally got good enough at it in the mid-90s to reach a very surprising result, which was that the high redshift objects were not too close. They actually were too far away. They were too faint. And this was found from a pair of teams looking at high redshift supernovae, and they found that the expansion rate appeared to be accelerating. Now this is a completely bizarre idea, because if you throw a ball up into the air, you expect that gravity is going to pull it back down to the ground. And what we found is that no, as you throw the ball up into the air, it actually accelerates away from us. Gravity appears to be not enough to stop this acceleration. This is very weird because in our standard knowledge of the forces of the universe, gravity is the dominant force on large scales. It should be pulling on things, and yet something in the universe is actually pushing things apart. So this came to be labeled as dark energy in association with dark matter, even though they may be totally different things. And the idea is that there's some unknown energy filling space that's causing things to be pushed apart. Now, I usually joke in these talks that the phrase dark energy actually overstates our knowledge by a factor of 2, because all we really know is that the material is dark. We don't actually know that it's energy. So we will see how this might happen. But so again, what's happening is that At early times, you have some kind of deceleration, but now at late times, it's actually getting faster. The speed is getting increasing. And that means that you have more distance, more look-back time, and more distance to a given redshift. So the supernovae appear to be too faint. So this leads us to a very strange conclusion about the universe, that when we think about the unknown part of the universe, it's not only that we don't know about the dark matter, we also don't know about the dark energy, which today is making up about 3/4 of the material of the universe. And we live only in this little piece of the atoms, and in fact, the stars are even a small fraction of that. So we're really being outvoted in the universe 20-1 by this unknown stuff. So what's the cause? Well, there have been many possible explanations for dark energy that have been advanced. The most famous actually comes from Einstein, who speculated about something called the cosmological constant. And he wrote this down for reasons that quickly became seen to be sort of ill-posed or poorly inspired. But the idea stuck around, and so when people were looking in the mid-90s to try to explain their supernova data, they settled upon this idea of the cosmological constant as one possible explanation. But it's not the only explanation. It might be that there's some new force of nature. We know about the strong force, the nuclear strong force, the nuclear weak force, electromagnetism, and gravity. Maybe there's another force out there that we now are just finding on cosmic scales. Or maybe we misunderstand gravity. Maybe gravity is not general relativity. Maybe gravity is pulling on small scales, but actually pushing on large scales. That would be very strange, but could be true. There's lots of other ideas. If you were to line up all of the journal articles that have ever been written about explanations of dark energy, it'd be a very, very long set of articles on a shelf. But the problem is that all of these ideas have some level of exoticism. There is no idea out there that just by its intrinsic beauty compels people to think, oh, this is the right idea. With general relativity, we had that situation. General relativity had a few tests early on, but basically people really like it as a theoretical construct, and so it had it really speaks to us as in terms of the beauty of its mathematics. But we don't have that in dark energy right now. So we're left trying to figure this out from an observational point of view, and the way that we try to do this is by measuring very precise distances. Now, distances are historically a very difficult thing to measure in astronomy. If you look out at a galaxy, it's hard to tell whether that galaxy is a very luminous galaxy far away or a less luminous galaxy nearby. It's really hard to get a sense of distance because it's not like in this room where you're getting a little bit of a stereoscopic view. If you cover up one eye, it's harder to tell distance. So here it's in astronomy, everything is so far away that we can't play that game very well. So distances are very hard to measure, and for most of the 20th century, or at least the second half of the 20th century, astronomers were arguing about the distance scale of the universe at the factor of 2 level. One group said that all the galaxies were twice as far away as the other group. It was a very persistent argument. So we're actually now going to be trying to do this to 1%, and that's what we think we've succeeded in doing with the SDSS. So now to the main physics focus of this talk, which is this concept that's called the baryon acoustic oscillations, which is a very complicated word for an idea that I hope I can convey to you. And it has to do with sound waves that propagate in the early universe. So the idea here is that in the early universe, there's sound waves that propagate, and they create a distinctive scale in the clustering of galaxies. So there's galaxies are slightly more likely to be separated, pairs of galaxies are slightly more likely to be separated by 500 million light years than by 400 or 600 million light years. So there's a slight characteristic scale. And once that scale exists, then we try to use it by basically trigonometry. So if I tell you that I'm 190 centimeters tall, then you can figure out how far away you are from me just by bringing out a protractor and measuring the angle from my feet to my head. Right? So once you know the length of something, you can infer the distance to it by measuring angles. And astronomers are exceptionally good at measuring angles. We really like angles. So that's the story. I'm going to be saying it again and again here for a few slides, but that's the basic synopsis of what we're trying to do. So to get into this story, there's the idea of the cosmic microwave background. So the cosmic microwave background is the heat that is left over from the Big Bang. And we discovered it in the 1960s as a faint, hum in the microwave part of the spectrum. So waves about that big. Remarkably, the microwave background appears to be the same in all directions. So when you make a picture of the microwave background, it looks something like that. That's a picture of the sky on the microwave background, a rather boring picture. And this is really one of the most important results in cosmology, that there's this early universe that has a very simple, smooth form. This temperature of the microwave background is about 3 degrees above absolute zero. So it's a very cold temperature, turns out to be the most important thing in the universe. Okay, so sometimes important things are found in little places. All right, well, it's very, very smooth, but it's not perfectly smooth. And people immediately set out to try to measure small deviations in the temperature from one part of the sky to another. And they found that, lo and behold, when you turn up the contrast by a factor of 1,000, that you find small deviations. One part of the sky is a part in 1,000, 3 millikelvin hotter than the other side of the sky. Well, this turns out to have a boring explanation. It's because we're moving towards the hot spot and moving away from the cold spot. So this turns out not to be very cosmological. But if you continue and turn up the contrast to 30 microkelvin, so 30 millionths of a degree hotter in one part of the sky than another, you get this picture, which was taken from a satellite called COBE in the early 90s. And this is actually a picture of small density contrasts in the early universe. So we are looking out at the microwave background, which has traveled to us from a time 400,000 years after the Big Bang. We're looking out at a sphere that we sit at the center of, and on that sphere, we are seeing tiny density perturbations from one spot on the sky to another, part in 100,000. Well, that picture had very poor angular resolution, and subsequent experiments have tried to do better and better. This is a picture from the WMAP satellite that was released in 2003, and now you can start to see a lot of structure in that early universe. The baby picture of the universe has a lot of structure in it. Here's the most recent picture from the Planck satellite, the European Space Agency mission. And these perturbations, these small temperature variations, are very tiny, but they turn out to be extremely important. This is actually basically our best data set about the early universe and about the composition of the universe. So now we'll get into this question of acoustic oscillations. So if you take this picture and you kind of look at it and just, there's temperature fluctuations on long wavelengths, long angular scales, on short angular scales. But if you just look at this picture, there's a characteristic size of the blobs. Where there's just a characteristic size here. The blobs just tend to be about this big. Hot and cold spots are about a degree of angle on the sky. And this turns out to have a very important result. This is due to sound waves in the early universe. So we try to analyze maps like this by basically breaking them up into angular frequencies. So this is like taking a piece of music and figuring out how much of the music is being played at middle C, how much is at high F, how much is at a low A, and trying to figure out how much of each key on the piano is being, how intense the music is at each key of the piano. And when people do that, this is now labeling the key of the piano. So this is the lowest tones, the bass tones, this is the highest tones, the treble tones, and this is the amount of intensity as a function of frequency. So you can see there's a very characteristic peak here at 1 degree, but there's also harmonics. And this is basically saying there's a lot of signal at middle C, and also at high C, and double high C, and triple high C. There's a characteristic pattern here, which very much is the equivalent of the harmonics in a musical instrument. So if you think the data here, you can sort of see the third peak there. But now with the Planck data, you can count 1, 2, 3, 4, 5, 6, 7, 8, and if you squint at the yellow points, the 9th acoustic peak. So there really is, the universe has a fundamental tone in the microwave background sky, and you're seeing that fundamental tone and 8 harmonics of that tone. All right, so what's causing this? Well, I said it's sound waves. So what's happening here is this very important epoch called recombination. So as the universe expands, it's getting colder. And that means that if you reverse the process and think about the early universe, there's a point in the early universe where the universe is finally hot enough and dense enough that all the atoms in the universe are ionized. This is this early epoch of the ionized universe, which then, when the universe finally gets to be about 400,000 years after the Big Bang, the universe has cooled enough that it becomes neutral. So this difference between an ionized and a neutral gas is very important. The gas in this room that we're breathing is dominantly neutral, and that's why the light is able to travel freely, why we can see each other. If the atoms in this room, in the air, suddenly became ionized into a plasma, among the very bad things that would happen would be that we would not be able to see each other. So basically, you have this period before reionization when the universe is ionized. So this is very important because if you take some of that gas, that plasma, and you compress it by gravity, then the photons, the light, are trapped inside of this compressing region. And as you compress the photons more and more, they build up their pressure. Photons carry a little bit of pressure, light carries a little bit of pressure. So this is like taking a balloon and trying to squeeze it. You're going to increase the pressure and pressure and pressure, and the balloon's going to push back out. And so that region will push out, it will actually expand too far, become a little bit too cold, a little bit under-pressured, the rest of the universe pushes back. So basically, in this early plasma, anytime you set up any kind of density perturbation or try to push the material around, it responds in the form of sound waves. So these are exactly like the sound waves that are traveling in this room. You know, sound waves travel because of an oscillating behavior of compression and rarefaction, peaks in the gas. And the same thing is happening in the early universe. Well, this all stops at recombination because now if you take some of that gas and squeeze it, gravity wants to keep going. And the photons are no longer talking to the gas because it's a neutral gas, the photons can just leave. They can just travel away. So now you have any little bit of collapse leads to runaway collapse, such as what might form galaxies. So you have this major transition in the early universe where initially the perturbations are stabilized and oscillate as sound waves, and at late times they form runaway collapse to form the large-scale structure of the universe. So here's a little picture to show why this is so important for the story that I'm telling tonight. So if you imagine a universe that's smooth except for an overdensity, an initial overdensity at a single location, then that initial location is overpressured. And as the universe expands, that overpressure is going to try to equilibrate by driving a spherical sound wave out into the medium. So this is very much like if I had a balloon, a high-pressure balloon up here, and that's the initial time, and now I pop the balloon, there's going to be a sound wave that travels out to you. And of course, it doesn't travel instantly. It travels at some speed, as if, like lightning and thunder. It takes some amount of time for the sound wave to travel. And the sound will travel a certain distance by the time it reaches recombination. So the wave will travel out and it stalls and it produces a spherical shell that today has a radius of 150 megaparsecs or 500 million light years. Megaparsecs is a funny astronomy unit, but you can think of it as 500 million light years. So again, it's like there's a bolt of lightning, a clap of thunder goes out, but at some point the sound speed drops and the thunder just freezes at some location. And it will travel out a distance of 500 million light years. Well, this is very useful to us because the initial overdensity will produce extra galaxies because of the extra dark matter there. This extra shell of gas and photons that travel out will also create extra material and will tend to promote galaxy formation. And so we predict that pairs of galaxies, you could have a galaxy at the center and a galaxy somewhere out on the shell, and pairs of galaxies will therefore be preferentially separated by this distance of 500 million light years. So it's a very strange thing. Now, 500 million light years is a very long distance. Even for astronomy circles, it's still a long way. So it's the distance that obviously light could travel in 500 million years. The age of the universe today is only about 13 billion years. So it's a fair fraction of the age of the universe that this is affecting. Now, the reason that this is so useful to us is that this distance of 500 million light years is something that we can compute very accurately. I think I won't, for the interest of time, I won't get into how, but we can actually, from measuring the details of the microwave background, that frequency spectrum of the microwave background, we can actually measure this scale extremely well, and today we know it to about 0.3%. So the universe has been very kind to us. It's given us a characteristic scale in the clustering of galaxies that we can calibrate to 0.3%. So it's as if the universe has given a standard object 190 centimeters high and has told us the height to whatever that is, 6 millimeters. Okay, so we're now going to use this to measure distance. Now, unfortunately, this is tricky because the toy model I explained was a perturbation at a single location. In fact, every location in the universe starts off with some pressure perturbation. They all throw out their spherical sound waves, and we're left trying to sort out the behavior. So it's as if you take, not just a single pebble to throw into the pond to watch the nice circular wave. It's like you take a whole handful of stones and throw them in the pond, and every stone has produced its little wave going outwards, and you're left trying to figure this out. But this is actually what signal processing techniques are really good at, and I'll try to show you a little later about how we do this in practice. But the main problem is that this distance of 500 million light years is a very large distance. And so to measure this, we have to map very large parts of the universe, which brings us to the second part of the talk. How do we map the universe? How do we figure out where all the galaxies are and make these maps? And the way we primarily do this is by measuring the locations of galaxies. In principle, you'd like to measure the location of dark matter, but dark matter is dark, and so we don't do that very easily. Instead, we try to measure the locations of galaxies. And we start by making two-dimensional maps of the sky, taking pictures of the sky to find galaxies. That tells us about where the galaxies are in 2 dimensions on the sky. But we then need to turn that two-dimensional image into a three-dimensional image. And the way that we do that is with spectroscopy. So we basically are going to take the light from each galaxy, spread it out into a rainbow, and measure where these key quantum transitions are to measure how fast the galaxy is moving away from us. And that allows us to make these maps. So the largest maps today use about 1 million galaxies. And they come from something called the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey is a project that started in 1990, so really quite a while ago, 25 years ago. Started taking data in 1998, and it's still running. This uses a dedicated 2.5-meter telescope, shown here, which is in the mountains in New Mexico, in the US. It's produced the world's largest compilation of astronomical spectroscopy. So we've measured about 4 million different objects, and the project has been well supported over the years. We have a really wonderful collaboration. The Sloan collaboration now totals about 1,000 scientists across the world, including here in Spain, and many different backgrounds, lots of different skills. We're surveying the sky, so there's a lot of different interests that come together with interest in this data. I'm only explaining one of them today, but there's a lot of different reasons why people try to join together to do this survey. Okay, so here's the main telescope, 2.5-meter telescope. So by astronomical standards, this is not a very big telescope. It's a nice telescope. What makes it unusual is that it's a very wide field of view. So it can survey the sky quite rapidly. The big telescopes tend to only be able to see a very small fraction of the sky. We can look at a bigger fraction of the sky, which has been very effective for us. So the survey started by doing imaging. So we had to image the sky. We didn't know well enough where the galaxies were to try to do our spectroscopy. So we imaged the sky. Here's an example picture of a nice nearby galaxy, globular cluster. Here's a pair of interacting galaxies. Here's a nice nearby group cluster of galaxies. But these are just highlights of the imaging. The imaging really is very systematic. We really are imaging the whole sky. So one view of the data is this view, where we've taken the entire image. This is now imaging about a quarter of the sky. So basically, like if you were to go outside in April and look up, it would be like all the sky above you, away from the Milky Way. And this is actually removed. We've edited out all the stars and just shown you the light from the galaxies. So you can see the galaxies here. Now you can actually see some of the large-scale structure of the universe here. There's a big blob over here, and some other regions, and so there's actually some large-scale structure here. The galaxies are not scattered randomly. They're clustered, and this clustering is telling us about the processes that happen in the early universe. Here's a picture of the other side of the galaxy. So if you the last slide was the part when you have the galaxy sort of at the equator and you look up. The next part is at the galaxy at the equator looking down. We didn't cover quite as much of the sky. But all told, we've imaged about a third of the sky, and all of this data has been released to the public. It's a very large public archive that we've made. It's hard for these pictures to express how much detail there actually is in these images. If you take a little block here and blow it up, you get to this region, you blow it up again, you get to this region, you blow it up again, you get to this region. And I don't think from where you're sitting you can yet see the detail in the maps. So this is over 1 trillion multicolored pixels of the sky. It's 5 colored pixels. So it's a 1 trillion pixel map of the sky trying to image what's out there. Okay, so that gets us our 2-dimensional map. But now we want to try to go into the 3rd dimension. And to do that, we need to measure spectra. Well, spectra are very expensive because basically we have to take the light from each galaxy, and instead of just trying to make an image of it, just collecting all the light, we're going to take the light and spread it out into a rainbow. And in detail, we measure about 1,000 different colors of that rainbow, trying to tease out these small variations in the spectrum. So this is much more expensive, whereas the images only take us a minute on the telescope. The spectra take us about an hour. And so we're more limited in how we do that. So we do it with something called multi-fiber spectroscopy. And basically what we're going to do is at the focal plane of the telescope, we're going to place a plate. And I brought a plate here. So this is a plate that was used at the telescope a few years ago. And I think you can probably see, if I rotate it around, you can see the little holes. Can you see the holes from where you're sitting? So you can see the little holes in the plate. Actually, the next picture on this maybe shows that a little better. So those little holes. And into each of these holes, we're going to insert an optical fiber. So this plate would sit at the location, at the focal plane of the telescope. So basically, the light would come down, hit the primary mirror, bounce back up to the secondary, and come down and hit the plate. If the plate were coated with photographic film, then you would actually make an image of the sky at the location of the plate, and it would be an image that would have a diameter about 6 times the diameter of the moon, about a 3-degree field of view. Well, this plate is not made of photographic film. Instead, it's made of aluminum, and we've inserted optical fibers at very precisely known locations, and the light from the galaxies will hit that optical fiber and enter into that fiber and run off to our spectrograph. So we can basically take spectra of 1,000 objects at a time, very carefully chosen across the plate. So the holes have to be drilled to 10-micron precision. The optical fiber that's being inserted is about the thickness of your hair, about 100 microns, and the locations are known to 10 microns. So this plate, although it seems like a big, rough object, is actually very precisely machined to give us the exact location of the galaxies. So basically what we've done is we've looked at the images, we've figured out the galaxies that are most interesting to us. Some of them are galaxies, some of them are quasars, some of them are stars. But we figured out the 1,000 objects we think are most interesting. We figured out where their light is going to fall on the plate, and we've drilled a hole there. Now, how do we get the fibers into the holes? So, done by hand. So this movie is sped up by about a factor of 40, but basically it takes them about 45 minutes to plug the fibers. Here are the people who actually plugged the fibers. Their record was 100,000 fibers in a month. So that was a tough month. The fibers then the thing goes onto the back of the telescope. The green boxes are the spectrographs that will record the light. So I'm going to pass this around so that you can see it. So you should just think that when you're looking at this, that basically you're actually looking at the locations of galaxies that we've recorded from the sky. This is This is a very hard piece of metal. You can't hurt it, I promise you. If you took it out and ran it over with your car, you might hurt it, but short of that, you're not going to hurt it. You could hurt the head of the person in front of you. So please be very careful as you're passing it around not to bonk, not to hit the head of the person in front of you, because it has a sharp edge, and it actually weighs about 5 kilograms. So it's not, but it's fun. And I'm happy to take questions at the end about other features of the plate, but I could spend the whole rest of the time talking about the plate. Okay, so this is a movie that will run to show you how we then observe at Apache Point every night. So first, the plates are actually live in these cartridges, which weigh about 300 pounds, so about 150 kilograms. And because they have to hold the plate in an extremely rigid location. So they get taken out to the telescope. They actually get inserted onto the bottom of the telescope. Dimitri will slide in here to bring the plate in. So the last plate's coming out, the new plate's going in. Pull it away. And then that goes back on the cartridge lift. That thing sits in the open air so that it equilibrates the temperature of the night to the night air. So you saw the building rolling off. This is an unusual telescope because it doesn't have a dome that protects it from the wind. Instead, it has this building that rolls off. What you're actually seeing in the telescope, the slats on the side of the telescope, are actually the windscreen, so that when the wind blows on the telescope, it's actually blowing on the screen, and the screen may jiggle, but it's actually not connected to the telescope. The telescope lives inside the screen. The telescope points, and the windscreen moves around to keep it to stay synchronized and keep out of the way. So we're now observing at some location on the sky. This is obviously greatly speeded up. We'll sit there for about an hour observing that particular location on the sky. And when that's done, then we will close up, take a bunch of calibrations, hurry up, change the plate. OK, ready to go again. So that's what we do. On a good night, we'll observe 9 plates. Most nights are not good. Most nights it doesn't work quite that well, but the best nights we observe about 9 plates, 9,000 objects. I will speed up here, probably skip the last bit of the movie here. But what else to say about it? Oh yeah, so when you're done observing that plate, that was for that particular spot on the sky, so we don't use them again. So they come back and we do outreach activities like this, or send them to schools or whatever, but we can't use them again. So we will make that plate very precisely machined. We'll use it for about an hour, and then we move on to the next one. And in the course of 15 years of the survey, we've observed about 6,000 of these plates. OK, well, with that, we've made maps of the universe, which may or may not get here. Come on. There we go. OK, map of the universe. So this is a piece of the universe. This is about 3% of the survey data, about 20% of the area of the survey. So you should think of it as like 4% of the sky. And the yellow here, the color is telling you about different distances from us. The yellow objects are a little bit closer than the red objects. It's actually a pretty thin slice of the universe, but this is now over a pretty big chunk of sky. So this is 6 billion light years across. The slice is about 500 million light years thick. And you can see the large-scale structure. The galaxies are not scattered randomly. If you remember back to that picture I showed you that looked like the squashed orange spider, like you couldn't really see very much large-scale structure. But now, once you actually can see it in 3D, now the large-scale structure is very clear. And you can see the clusters, voids, these long filaments. Here's a big area, supercluster area. So these are very large scales. And we're now trying to figure out how we're going to measure the correlations and the subtle patterns that the early universe has left for us in this picture. So I'll show you now a movie of that, where this is now a chunk of the sky, about 4% of the sky. And I'm now going to show you a thin slice and have that slice move away from you as the movie goes on. So it's the same chunk of the sky, but now you should think of it as like a piece of a slice moving away. So that's shown here, where Earth is here and we're looking out, and the black is the little region that we're going to be looking at. And as the movie goes on, the redshift will increase. We're going to be looking further and further away, and you'll see the large-scale structure change because you're changing, sort of tomographically, you're changing how the slice interacts with the large-scale structure. This circle is a radius of 500 million light years. So this is this acoustic oscillation pattern that we're looking for. I included here because you'll see that as you as the picture moves out to higher redshift, the circle gets smaller because you're looking at an object that's further away, so it looks angularly smaller on the sky. Points will appear faint and red, they brighten up to dark black, and then they fade away to light blue. But basically, if you just look at different parts of the sky, you'll see the large-scale structure change as, basically you have this cosmic web of structure, and you're basically sliding through a two-dimensional slice of that. If you look carefully, you can see the large-scale structure getting smaller on the sky. The voids appear to be angularly smaller. That's real, that the structure appears smaller far away. We're now getting to the thick part of the survey, about redshift of a half, so about halfway back to the Big Bang. And now we're getting to the edge of the survey. The start will start to thin out because the galaxies are getting too faint for us to observe well. So that's about 20% of the survey data. Okay, now how do we actually use this? I mean, great. So you see a picture. It's a very complicated picture. But how do you actually learn about the early universe from it? So we do this with something called a correlation function. There are lots of different statistics, but I think the one that's easiest to explain is the correlation function. So here, we imagine sitting on one point on the survey, center up on one point of the survey, and now count the number of galaxies that sit in an annulus indicated by this gray zone, and repeat that count as a function of radius of the annulus. And now repeat that, taking every point in the survey as a potential center. So this is equivalent to summing up how many pairs of galaxies sit at a function of how many pairs of galaxies have a separation of a given scale. Basically, you're making a histogram or a binning of the number of pairs as a function of separation. And when we do this, we find this bump at a scale of 100 h inverse megaparsecs, about 500 million light years. So this is the bump that comes from the early universe, this Baryon acoustic oscillation bump. And this was a very exciting result in 2005 because it gave us a very direct connection between the pattern that we were seeing in the microwave background, those harmonic peaks in the microwave background from the sound wave that we see 400,000 years after the Big Bang, to the clustering of galaxies that, although they're far away from us, are still 10 billion years later. So we have this very direct connection between the early universe, 400,000 years after the Big Bang, and the galaxies that we see 10 billion years after the Big Bang. So this led us to propose the third epoch of the SDSS, SDSS-3, to try to use the telescope over a 6-year period to make an even bigger map of the universe, which is the data I was showing you before, but an even bigger map to try to really measure this very, very well. And this is the current data set from that. So here is this acoustic bump, acoustic peak in the data. And we use this now to measure the distance of the distance, in this case to redshift of about a half, to 1% precision. So we basically have used the scale that the CMB has calibrated to 0.3%. We've now been able to measure it to 1% in the spectrum in the clustering of galaxies. And we've been able to do it at a variety of redshifts. So basically, you should imagine that you're seeing some structure in the microwave background. We see some structure at redshift of a half, see some structure at redshift 0.3. Other parts of the experiment have measured it even earlier times. So we've been able to map, using this characteristic scale, been able to map distance as a function of redshift, and thereby use that to say things about the dark energy. Here's an example of such a plot. So this is redshift and distance, and here are the measurements we've made, along with some measurements that were made from 2 telescopes in Australia. And that's the measurement of how far away objects are as a function of redshift. And here is the prediction from the microwave background for a very simple cosmology, which I'll explain in a minute. So basically, the data really fits together very well in cosmology. We made this prediction from the early universe, the data 400,000 years after the Big Bang, and this allows us to predict the distance scale more recently, and it goes right through the points. A remarkable thing about cosmology now. If you zoom in at the residuals, things are matching to, of order of 2%. Really great agreement between the predictions from the early universe and what we measure today. And now what can we learn from it? So one thing we can do
is to try to measure the curvature of the universe. So in general relativity, the universe may have curvature. Curvature is a little bit funny. You hear about in general relativity the idea that space-time is curved and that gravity is the result of things moving on a curved surface. Well, it turns out the surface can be curved as well. And so you could have a universe which is flat. If it's a universe were two-dimensional, you could think of it as flat like a piece of paper. Or the universe might be spherical, or it might have this crinkled shape like a saddle. The curvature is basically a statement that the circumference of a circle in the universe may not be 2 pi times the radius. Of course, when you're learning Euclidean geometry, you think that if you go out to some distance and with some radius and you try to measure the circumference of a circle of that radius, you get 2 pi times the radius. Well, it turns out that if you do that experiment on the surface of a sphere, you don't get that answer. If you're a traveler and you walk from the North Pole to the equator and then go around the equator, you will go around a distance which is smaller than the distance you walked from the North Pole. So the acoustic peaks give a really wonderful measurement of this so here's a plot of the amount of matter in the universe, the amount of dark energy, and the flat universe line is this dashed line here. And when you put just the acoustic information together, it marks you right on that line. So we've made these beautiful measurements of the distance at modest redshifts with galaxies out to the microwave background, and the universe is astonishingly close to flat. This is one of the key predictions from the theory of inflation, cosmic inflation. And so, yeah, it's just being confirmed in beautiful detail with these kinds of data sets. But the other thing we try to do is measure the properties of dark energy. And the famous model for dark energy is the cosmological constant. That means that the dark energy density should be the same at all times. It's constant. But maybe it's not so. Maybe dark energy is changing in time, and that would have an impact on the density, so we'd like to measure that. And we tend to parameterize this by this parameter W, where W of -1 is the cosmological constant. And that would give different predictions for this curve, for this graph. I showed you before this graph with the pink lines, where that was the flat universe with the cosmological constant, the simplest model. Here's a model that would fit the data if the universe fit the microwave background data if the universe was 1% curved. This is a model that would fit the data if the dark energy had evolved in density by a factor of 2 over the last half of the age of the universe. You can see those are not good fits to the data. So the data, the galaxy data is now giving very precise measurements of how flat the universe is and how constant the dark energy is. 2 key predictions of the simplest model. So when you make a plot of curvature and W, here's the flat universe, here's the cosmological constant, the data is really zooming in on this simplest model. So that's been a major result of the current data sets. Okay, so getting to the end of the talk here, and we're really at a crossroads in astronomy. It's just a wonderful point in cosmology where we have a very concrete and simple and in some ways elegant theory for how the universe works from an age of 1 second after the Big Bang until today over a range of order 100,000 in scale. It's a very predictive model. And it's really a triumph of astronomy and cosmology over the past decade that this model has been tested so exhaustively and in so many different ways. And it seems to be passing these tests quite well. And that theory is not just a statement about cosmology, it's also laying all the groundwork for investigations of the evolution and formation of galaxies, of all kinds of structure in the universe. It really is the initial conditions that we now start our calculations from. But it has this remarkable aspect to it, that it has not one, but 2 unknown types of material in it, the dark matter and the dark energy. And our theories for these work very well, but we don't actually know what they are. So it's a very strange situation to be in, but it's a great opportunity for the coming decade to try to explore in more detail both what dark matter and dark energy are. These are the pressing questions in cosmology today. And there's a wide variety of experiments that are going on now to try to improve these maps. So this idea of mapping the universe is a very powerful way of making progress on this. And we're expecting improvements in the coming decade of factors of order 100 in our ability to map the universe, both in terms of volume and number of objects. Experiments such as these. This is the European Space Agency mission Euclid, mission called LSST. The one I'm involved with here is called DESI. There's many others. The Dark Energy Survey that was talked about by Gary Bernstein 2 weeks ago is another one. But this is just giving us an enormous reach on cosmology that we're now starting to harvest this data and learn from it. So to conclude, acoustic oscillations provide a very robust way to measure the cosmic distance scale. It's very simple physics from the early universe, and it leaves a very clean signature in the clustering of galaxies that we're able to extract with these very large maps. And it's now become a very important tool in the study of the cosmic distance scale. It's one of the key ways we try to measure the cosmic distance scale. Within SDSS, we've used the peak to measure distance to the percent level accuracy, really unprecedented in astronomy. And this gives excellent consistency with a flat cosmology with a cosmological constant. So two very simple ideas about what might be out there. But there's just lots of opportunities left to explore in cosmology for the next generation. I'll invite you to learn more about the survey at www.sdss.org and just leave you with this picture. And I'm happy to take any questions that may come up. Thank you.